Thank you so much. And first of all, thank you for the organization of the event and for the invitation. It's an honor. I will talk about mainly three different areas. The first one is a paper about climate change projections of temperature-related mortality in Europe. The second one is about ongoing research about adaptation to climate change, and the final one is the one that here is specified, which is climate predictability and the use of this climate predictability to develop early warning systems. In all the cases, it's based on the relationship between temperature and mortality. We are a group in Barcelona Institute for Global Health in which we are, well, we have a strong bias towards climate modeling, climate data, and the use of different data sets, climate data sets for the development of epidemiological studies. And so this is the core of the talk. I'm going to talk a bit about different timescales of these data sets, from climate change projections to weather forecasts at very short lead times. So the first one is projections of temperature-related mortality. It's a study that was published last year. I always put the pictures of the people that deserve the credit. Erika Martinez Solana, that led this study. In this study, we used a large temperature and mortality data set for 15 years in Western Europe. And we modeled the associations using the same techniques that were explained in the previous talks. The association between temperature and mortality in the historical period. This is shown in the plot on the left. In this plot with increasing mortality risk for temperatures above and below the minimum mortality temperature. In this study, we also showed the relative risk at the cold and warm percentiles, and we found that the risk is relatively homogeneous in Western Europe for cold, but instead for heat it is quite heterogeneous with much larger risks in the Mediterranean, in Portugal, in Spain, in Italy, and in Croatia. Overall, the attributable mortality due to cold temperatures is 10 times higher than the one for heat. We use these associations to do the projections according to different scenarios, climate change scenarios. In this, well, here I show the relationship for the evolution for temperature anomalies, and by using the epidemiological models, the projections for the attributable mortality expressed as a percentage of the total raw mortality. We see the increasing temperatures in Western Europe for the different scenarios, and this corresponds, when we apply these epidemiological models, to these curves. Here it's shown the trend for the historical period, and in all the cases we see that there is a minimum in the mortality at present time. I wrote here optimum counterfactual climate because, of course, this corresponds to projections in which we include no adaptation. So we are using the associations in the historical period. We have very different projections at the end of the century. In the lower emission scenarios, we have this minimum is observed during the whole century. But instead, in the higher emission scenarios, we have a very clear upward trend. This can be seen as maps. So these are the maps comparing the differences in attributable mortality for the end of the century minus the historical period for the highest emission scenario. The left is the total, which is the sum of the contributions from cold days and from warm days. We see for cold, again, that there is a quite homogeneous pattern of change, a decrease in cold attributable mortality, and for heat, we have instead this heterogeneous pattern between the southern and central Europe. Together, this defines these patterns with a very clear north-south pattern. This is mostly due to differences in vulnerability in the historical period and differences in climate change projections, both together. In a subsequent study led by Marcos Quijal Zamorano, we analyzed we took the same simulations, the same climate change projections, and we analyzed the contribution of the different types of extremes, extreme heat. We divided extreme heat by the one that has been observed in 2020, and the other one that has never been recorded in the past. These are so in red we show the contribution to heat, to the mortality. Heat attributable mortality is a function of the decades for the different scenarios, the mildest and the highest emission scenarios. And we see that there is a huge diversity in this contribution of currently present-day unobserved extreme heat, depending on the level of emission. This is again, of course, in a scenario in which there is no adaptation. And this, again, we can see these projections from a different perspective, and this one is the changes in the seasonality of temperature-related mortality. In the historical period, we have much higher mortality in the winter months, even in the spring and autumn, and low mortality in summer. And this can potentially, if we assume no adaptation, can change so that the contribution of summer is much higher. This, of course, this is a scenario that is very likely that do not happen because it doesn't take into account adaptation, and that motivates the second part of the talk, which is the project Early Adapt that started last year. It is motivated by previous results from Isham Shebak, in that he analyzed data sets of cardiovascular mortality and respiratory mortality for Spain. And he looked at the changes through time of the vulnerability of the relative risks. So the top row corresponds to cardiovascular mortality, the bottom row corresponds to respiratory mortality for men and women and for different subperiods. So in red is the former period, in blue is the later period. And we see differences not only between men and women, but also between diseases. For example, for cardiovascular mortality, we see a relatively homogeneous decrease as a function of temperatures, but for respiratory mortality, we see a much larger decrease in the mortality attributable to cold temperatures. So we deduce that there are very large heterogeneities in this decrease in the vulnerability to both heat and cold, and this is only for Spain. This can be seen among European societies. It can be seen among different age groups and among different sociodemographic groups. So this same study also showed the evolution of the MMT and the seasonality in this same period. This shows for respiratory mortality. And in the case of respiratory mortality in Spain, we see a clear decrease in the minimum mortality temperature, which happens before in women and in the elderly than in men and younger age groups. But it happens at some point in all the groups. And this change, both the change in the reduction in the relative risk due to cold and this change in the minimum mortality temperature, the MMT, defines the change in the seasonality from a seasonality dominated by mortality in winter to one with mortality in summer. All these changes motivated the project Early Adapt, which is still in the first year. We are now collecting data sets. The purpose of this project is to describe the drivers of, let's say, adaptation, but here adaptation refers to general socioeconomic progress or just simply decreases in relative risk due to temperatures. To analyze the drivers of this adaptation, so the changes, the trends in the vulnerability, by doing a comparison both in space and time. So we are collecting a format homogeneous data set for European countries in which we are including several daily health outcomes, mostly mortality, hospitalizations, and occupational accidents, different environmental exposures, climate variables, air pollutants through a collaboration with the Barcelona Supercomputing Center, desert dust, and winter infectious diseases. And the key point here is the compilation of societal data in which we pretend to model macroeconomic cycles, the inequality in the social structure of societies, differences between countries, changes in demography, and inequalities like the gender gap. The objective is to have a data set, a mortality data set that allows us to do these spatial comparisons. The objective is to obtain daily data for at least 30 years, both for regions and for cities, just to be able to compare also rural and urban settings, and by socio-demographic groups, for example, age, sex, and also the causes of death or disease. That's, of course, a very risky objective. We've been saying that that's a very challenging objective, and so we are trying to maximize this criteria in order to get this database. In parallel, we are also compiling data sets. The first one was about daily time series, mostly, but we are trying to obtain data sets to do a small area analysis. This is the example for Spain, Catalonia, and Barcelona to look at national, regional, and city factors. For example, if air pollution is a factor that affects the vulnerability of the populations, then to study at the corresponding spatial scale, to study these factors at the corresponding spatial scale. To do that, we are developing epidemiological models based on previous work from the project ClimateFit.City, which was done in collaboration with the Barcelona Public Health Agency, in which we took urban climate. This is a land use map based on the local climate zones. This is a simulation of temperature for, this is Barcelona, the city limits, and this is the Barcelona metropolitan area. We did simulations based on urban climate models at a high resolution, and we crossed these exposures with individual mortality data sets from the Barcelona Public Health Agency. And to model that, again, this is Marcos Quijal Zamorano. We are in collaboration with Marc Marí del Olmo from Barcelona Public Health Agency. We are developing Bayesian spatial models to model the associations at each neighborhood of Barcelona in order to get the associations based on a Bayesian approach. We are doing that for Barcelona, but the objective is to extend it to for example, Catalonia. There is interest from for example, the Barcelona metropolitan area to develop vulnerability indices based on health data in order to decide where to put money in order to increase resilience and adaptation in the metropolitan area. So, for example, where to put a climatic refuge. So far, all the money is spent based on sociodemographic factors of vulnerability, and here we will try to develop indicators that are actually based on health outcomes. And finally, well, this referred to long time scales, climate change projections, adaptation. Finally, I would like to cover some work that we are doing at the other end of the spectrum of the time domain, which is based on weather forecasting. The objective is to use the predictability of the climate system in order to drive fit-for-purpose early warning systems of temperature-related mortality. This is motivated by the revolution in the quality of numerical weather forecasting. This is a map, that's a forecast scheme of a geopotential height at the middle troposphere, which is a key variable for predictability both in the troposphere and at the surface. This is the year in which the forecasts were done, and this is the predictability scale, both for the northern hemisphere and the southern hemisphere for different lead times, 3, 5, 7, and 10 days in advance. One important feature is the convergence between the two hemispheres, thanks to the improvements in data assimilation, which improves the initial conditions of numerical weather forecasting. So we decided to use weather forecast from the European Center for Medium Weather Forecast, a forecast that go up to 15 days. And we use the epidemiological associations that I showed before. This is the observed temperature versus the forecast temperature for summer and for winter days at lead times 1, 5, and 9 days ahead. And we see the very close correspondence, as it is expected, that is fading away as the lead time increases. We have also higher predictability in winter than in summer. We have the other plot, which is if we apply the epidemiological models to transform the temperature forecast into mortality forecast, we obtain these plots. This is observed mortality versus predicted mortality at the same lead times for the same seasons. If we change, we see that there are some differences in between the two plots. We have some similarities. We have a decreasing scale as expected. We also have higher predictability in winter than in summer, also in mortality. But we have some differences. The decay, it is much stronger than for temperature, the decay in predictability. We can see here the clouds are, the correlation is much higher than in here. And this drop in predictability is much higher in summer. This can be summarized in this plot. This is the anomaly correlation coefficient, which is a measure that is used to evaluate weather forecasts and climate forecasts as a function of the forecast lead time. This typically goes from, values go from 0 to 1. 1, it means perfect forecast. And we see this decay. This is winter, this is summer, temperature in red, mortality in blue. And we have this decay in the predictability. For winter, we have very similar, and we define the predictability lead time, the lead time in which the curve crosses the 0.6, which is the typical threshold that is used in climate forecasting. We see the predictability lead time is very similar in winter, both for temperature and mortality, but we have lower scale in summer compared to winter, and we have much larger differences between temperature and mortality. The next step was to look at the spatial pattern of this predictability lead time. This is just for summer. I'm not showing winter because it's much more the two maps are much more similar and more homogeneous. This is the most interesting of the two. This is the predictability lead time for temperature and for temperature-related mortality. And we see these differences in the red is higher predictability lead time, so scale blue is lower. And we see these differences between the two variables. And we define the loss of predictability due to the epidemiological transformation as the difference between the mortality one and the temperature one. Each dot here is a region. And we see that there is a relationship between the loss of predictability and some variables. Here I show the number of heat waves, the number of heat days, not heat waves, which is equivalent, well, it's the reverse of the minimum mortality temperature percentile. The more heat days, the lower is the percentile of the MMT. And so the regions with the lower number of heat days are the regions in which we lose more predictability due to the epidemiological transformation. And just to wrap up, well, just to conclude, the future work, the work that we are going to start in September are these two projects. I don't know if it's Catalyst or Catalyze, it hasn't been decided yet, and the proof of concept. In Catalyst, we are going to do a partnership with the Catalan Meteorological Service and the Catalan Public Health Agency in order to do an early warning system directly addressing the needs of the Public Health Agency in order to modify the heat prevention plan of the Catalan Public Health Agency. The objective, the final objective, is to deliver to the Meteorological Service the system and all the tools so that they can run every day the forecasting, the early warning system. The other one is the proof of concept, which is a project that is oriented towards, it's not oriented towards the end users, but to the generation of a product that is continental scale and that can give the warnings customized to the different socio-demographic groups. So men, women, elderly, poor neighborhoods, rural, urban, deprived groups with deprivation, etc. All that the epidemiological model and the health data set allow, it will be taken into account in order to customize the physical information of the weather forecasts. And that's all. Thank you so much.